Hello everyone. My name is Thomas Kugel. I'm a first year PhD student at the University of Würzburg at the chair of TP3. And today I'm very glad that I'm able to present at least some preliminary results from my project with my collaborators, these being Giuseppe, my advisor René, Wayne, and Jutsu. So this project is called Measuring Nonperturbative Symmetry Breaking with Symmetry-Resolved Relative Entropies. And I'm sure that after this teaser, all these words will have become at least a little bit more clear. So what is this project all about? Well, it's mainly about the role of local and global symmetries in quantum gravity. In the case of the latter, it's the lack thereof. And thus we would like to have a toy model, at least, of quantum gravity, which models black hole evaporation and also exhibits non-perturbative global symmetry breaking, since, as I said, this is one of the expectations we have for quantum gravity. And as it turns out, in our case, this is actually done very easily. So we just extend the usual end-of-the-world branes of the West Coast model by making them transform in a compact gauge group. And as it turns out, this is very easy in the case of the West Coast model because for the gauge sector, we will be using ABF theory. And shady gravity is also ABF theory if you rewrite it in first order form. And there we have a direct analogy how we can construct our n-boundary partition functions, namely fixed length geodesics correspond to fixed group elements, and fixed brane tensions correspond to fixed charges in G. And to convince you that this model already does something correct, we can actually have a look at one of the more simpler results, which is that of the quantum extreme surface result per charge sector. So we fix the charge and only take into account the fully connected and fully disconnected contributions for the n-boundary partition function. And then, we can take the n-to-1 limit and in the end reobtain a sort of minimal entropy prescription again. So what do we see in this case? We see that the entropy, both for disconnected and connected cases, is shifted by a representation dependent term. And actually it's shifted in such a way that larger representations will have a larger page time in the end. And now, of course, as in the West Coast model, we can also use the planar approximation and resum all these diagrams to obtain the resolvent per charge sector, which is shown below on the slide. And there you already also see that this is really just a rescaled version of the usual West Coast model resolvent. So we can already expect that up to shifts induced by the charge, the corrections to the entropy will be the same as in the old West Coast model. So how can we see this global symmetry breaking? Well, as Chen and Lin noted in their 2020 paper, there is a global symmetry in the West Coast model, which gets broken by the connected contributions. So if you include them, U and rho won't commute anymore. So the global symmetry is broken, and this shows itself in a rising relative entropy. Now, we were now actually able to compute the relative eigenvalue distribution of this model and express it in this remarkably ensemble independent form. So to sum it all up, what we get is that if we compute the relative entropy with the quantum extreme surface prescription, we will see that it is first 0 and then infinite after the page time. And similarly, we will see for the microcanonical one that before page time it will be order 1 and infinite after it due to a rank deficiency in the relative eigenvalue distribution from before. So there we will pick up a 0 eigenvalue, which makes this infinite. And in comparison to that, the well-behaved canonical case, which is small, also order 1 before the page time, and then grows asymptotically as log squared after the page time. So this concludes my teaser for the poster, and I hope to see some of you at the string conference so that we may discuss and share some ideas.